Hi class, we are looking at two sections, 21.8 and 21.9. First portion is converting mass to energy, mass defect, and nuclear binding energy. And the second one is nuclear fusion, the power of the sun. So let's get started. So when we look at a chemical reaction, one that not covering nuclear reactions, that is exothermic, it gives off energy. And this energy comes from the bonds between the atoms. Specifically, the chemical bonds in the products are overall more stable, which means they have less potential energy than the bonds in the reactants. When we look at nuclear reactions give off energy. So they also, the products are more stable, which is the same as the chemical reactions that we have been studying up to this point. So they also have less potential energy than the reactants. But the energy itself does not come from the chemical bonds. It comes from the nuclei, excuse me, it comes from the nuclei, the atoms themselves. So in a nuclear reaction, energy is emitted because a small amount of mass is converted into a large amount of energy. And that's where this equation here is E equals mc squared. This is Einstein's first proposed, he first proposed this in 1905. E stands for energy, M stands for mass, and is the mass, and C is the speed of light in a vacuum, and that is 2.99 times 8 times 10 to the 8 meters per square. Sometimes you will see that rounded up as 3.00 times 10 to the 8. So yeah, so you'll see that as this, or you'll just see it as 3.00. Depends on where you're looking at it. It's one of those things again. So the C squared term here has to do with the fact that there's a conversion of a small quantity of matter that produces a large quantity of energy, and that's where the square comes in. M is in kilograms. The units of E, these end up being kilograms per meter squared over second squared, which is equivalent to 1 joule. So during nuclear fission, some of the mass of the nucleus is converted into energy. Each mole of uranium-235 that fissions produces about 1.7 times 10 to the third joule of energy. A very exothermic chemical reaction produces 10 to the 6 joules per mole. So we're going to start looking at the energy and actual values from in this section. So, excuse me, mass defect and nuclear binding energy. So when a nucleus forms, some of the mass of the separate nucleons is converted into energy. So there's a difference in mass between the separate nucleons, and the combined nucleus is called the mass defect. And this is the amount of missing mass that's converted to energy, according to E equals mc squared. So energy is given off in the process, which means that the product is more stable than the reactants. And the binding energy is the amount of energy required to break apart the nucleus into its component nucleons. And remember, a nucleon is a term for both protons and neutrons, since that's what the particles that make up the nucleus. So binding energy is typically reported in nucleon per nucleon rather than per mole, which is something we'll cover here. So let's take a look at this problem here. And this is an AMU. AMU, we do not use AMU, so you'll see it'll be converted down here into kilograms because we want to get it into joules. And remember, if we look at joules, joules is 1 kilogram per meter squared over second squared. So if we look at the mass reactants of these here and we add them up, we can see that we have a total for the reactants, which includes the neutron, is 236.05258. And then the reactant product side, we have 235.86769. Now, that's not a big difference, but there is still a difference. So what we do is we subtract those. We subtract excuse me, the reactants and the products, and that leaves us an amount of 0.18489, and we're going to use a conversion to get it to kilograms, which we do. Now that we have the mass, we can now plug it into the E equals mc squared, the energy produced from this, and that gives us, here's our mass amount that was lost here. We have our c squared at speed of light, and it gives us our energy, which is 2.7593 times 10 to the negative 11 to the 11th joules. So the amount that we end up producing here is for one nucleus, which may not seem like a lot of energy, but you're going to deal with one nucleus, and we are dealing with a chain reaction and bombardment. So all of this ends up adding up. So we look at the next one here, and we have our reactants, a mass of reactants, and our mass of products. And we subtract the two, which leaves us with 0.03038 AMU. And we end up with a binding energy. So this one's just cut through, so it's not showing all the steps here. But we see a binding energy of 2.731 times 10 to the 13 joules per mole. Okay, so these are slides from another book, but they're doing the same thing. They're pretty much showing you exactly what you need to do for, just like the other two problems. Again, I have slides on it, so that's why I want to include them in here. So in these ones, they use, instead of AMU, they use U, which means the same thing, and 1 U is equal to 1 grams per mole. So here is asking to calculate the energy in joules per mole released in a fission reaction. So again, we take all the information and we plug it in, and it gives us the total mass, the total product, and the total reactant, and it gives us our information. Now in this one, you notice they did it with a negative sign, where on ours over here, they subtracted the reactants, the products from the reactants, and no negative sign. So this one's actually showing with a negative sign the change in mass. Now we take the change in mass, excuse me, and we're not done because we only have the mass, but we need to plug it into E equals mc squared. So in here we see that we take the mass that's been changed to kilograms per mole, and we take our speed of light squared, and it gives us the energy. And it's showing it's negative because it's so strong and powerful. It's, you know, but our book is not showing the negative sign. So I really wouldn't focus on the negative sign too much. Just know that this is where books, you know, you think that they're, you know, common all the way through, but there's little changes in them. All right, so calculate the energy released in a fusion reaction. Here it is. We have some isotopes of hydrogen in here, a helium and a neutron, and we plug them in. Excuse me, and the same thing. We are showing that this mass, change in mass, is 0.01888. Hopefully I said that right. We convert it to kilograms per mole, plug it in. So you can see that the theme is not changing here. We get the information, we end up plugging it into E equals mc squared, and it's telling us how much energy is being released in this. So now you can see that there's, we're looking at the curve of binding energy. And what this means, one thing I haven't discussed yet is these units of MeV. These are electron volts. So this is mega electron volts. This is what nuclear physicists use, where we tend to use in chemistry joules. So why is this used? Because this is typically energy in electron volts is reported in per nucleus. So this is adjusting to units to address actually what we're looking at here. So this graph here is shows the binding energy per nucleon, and it's plotted as a function. So we have the mass number here. So the mass number here would be A, and then the binding energy per nucleon. So you can see it's relatively, this yellow here is where the most stable nuclides are. So you can see it starts going up here. It reaches its maximum around 60, and that's the binding energy, the most stable. And then it starts to decrease again. So that's where we see the highest part. You can also see what is considered fusion, the parts where it's considered fusion, and where this is separated into fission on this graph. So again, when you look at the binding energy, the most stable is where this mass hits about up to 60. So you see that there's iron, and then what this graph is saying is probably around 60 is where it's most stable. And anything outside of this is not as stable as what's in this yellow. So now we're in the next section of nuclear fission. Nuclear fission reactions, this is my slide from another class. These occur at extremely high temperatures, and there's a temperature to give you an idea. They combine small nuclei into larger nuclei. They release large amounts of energy, and they can occur continuously in the sun and stars, producing large amounts of energy. So the fact that we're talking about the sun and stars should give you an idea of how much energy and how high the temperature has to be. In a fusion reaction, there's large amounts of energy that are produced from hydrogen isotopes, and they combine to form helium. Less waste is produced in a fusion reaction than in a fission reaction. So nuclear fission, again, combination of light nuclei, and it will form a heavier one. Along with fission, fusion emits a large amount of energy. The source is stars and the sun. It's a basis for hydrogen bombs. Produces 10 times energy per gram as fission with less problems. problematic products, excuse me, and it requires high put of energy to initiate this reaction. So it has to take a lot of energy to even get this started. So here's a slide here from, I think this is from my other class. You can see that it's dealing with isotopes of hydrogen, ending up producing the helium. You can see helium here, a neutron, and then a lot of energy. So this combines to produce helium, a neutron, and energy, which is exactly what I said. So here are the isotopes of hydrogen. We have tritium and deuterium. Deuterium is also known as heavy water. And you can see what goes in and then what's being produced on the outside. So this is just basically showing this. So nuclear fission reactions, we get two small nuclei and we form one larger one. And in doing this, we generate a tremendous amount of energy, even more than what we've discussed in fission reactions. I mean, think about it. We're talking about sun and stars here. Just the sun itself. The energy of stars comes from a series of nuclear fusion reactions. The simplest one of these is the overall effect of transforming hydrogen nuclei into helium. So we're just discussing alpha particles. Different kinds of stars are capable of fusing different nuclei depending mainly on the temperatures of the stars. And all of these are factors. It has to have high temperatures and a lot of energy. The sun, a moderately small star, which I like how they put that, of average temperature is powered by a following sequence of reactions. So we're dealing with hydrogen isotopes and helium isotopes. The positron released in the first reaction can then react with an electron to yield even more energy. The net reaction of this series of fusion reactions is the conversion of 4 protons into an alpha particle plus a great deal of energy. I'm not going to ask too many specific things about this if I do at all. Here's just a nice picture of what they're saying is happening here and what type of decay is going on. Okay, so hotter stars than our sun are able to convert protons into alpha particles via another series of reactions. And they can fuse heavier elements as well. Fusion reactions in stars often create heavier isotopes of hydrogen, and that's deuterium and tritium. Deuterium nucleus is known as deuterion, and a tritium nucleus is known as a triton. These are important reactants in the fusion reactions that form helium and heavier elements. So indicate which of the following describes nuclear fission or fusion. So this slide's from my other class. So a nucleus splits, that's fission. Large amounts of energy released, that's both. Small nuclei form larger nuclei, that's fusion. A hydrogen nuclei react, that's fusion. And several neutrons are released, that's fission. So hopefully this is a nice little reminder of which is which. Okay, here's an example from our book. Calculate the mass defect of nuclear binding energy per nucleon, and this is mega electron volts, for carbon-16, a radioactive isotope of carbon with a mass of 16.014701 AMU. So in this case, this is very similar to just adding everything together. We have 6, we take the mass of hydrogen, we have 10 of the neutrons, and then we're going to subtract that for this mass defect problem from the mass of carbon-16. This ends up giving us a mass defect amount of 0.118879 AMU. So we're just subtracting one from the other. Excuse me. Now this is a weird problem, but again, I put it up. This is exactly how it shows in your book. It's not showing anywhere where this information is coming from. Like, where do you get 6 hydrogens? Where do you have 10 neutrons? It didn't show that to me anywhere. So I probably would not ask a question like this. I mean, wouldn't, unless it gives you all the information for you to pull and be like, okay, where did this come from? But it's in your book. It's example 21.7. So I'm showing you how to break it down for a mass defect. So how to understand how to handle the problem. Though I don't like the fact that they just kind of didn't show everything, and I felt like this is missing some key things. Calculate the nuclear binding energy by converting the mass in AMU into mega electron volts. So it's giving you the conversion. So we take the amount and then we set it up for dimensional analysis and gets us this. Determine the nuclear binding energy per nucleon by dividing the number of nucleons in the nucleus. So we take this amount, and it's telling us that there's 16 nucleons. So we're going to divide that, and it gives us a unit of mega electron volts per nucleon. Again, this is in your book, but it really didn't go into detail about it says carbon-16, which is an isotope of carbon, but it's not really telling you it's not telling you anything until you get to the second part, which says calculate the mass defect as the difference between the mass of one carbon-16 and the sum of the masses of 6 hydrogen atoms and 10 neutrons. But it doesn't say where that information comes from, because it's not anywhere in the beginning of the problem. So I am aware of that, but again, this is in your book, so I'm giving you the problem, but I'm not happy with how this is presented. Okay, so comparing energy production, on average, the energies produced by fusion reactions are similar to or greater than fission reactions, and they are when you compare them per gram. So they have more energy per gram than, and we look at it as per gram than per mole over fission. Fusion reactions produce 10 times more energy per gram than fission reactions do. Fusion reactions produce over 10 million times more energy than chemical reactions. That sounds great, right? You gotta remember, we're dealing with the sun and the stars, so because neither the reactants nor the products of fusion reactions are necessarily radioactive, fusion reactors would be an ideal source of energy. Unfortunately, they have to be carried out in different conditions, which are still very difficult to have, and they haven't, based on the book, they can get it started, but they can't keep it going. So it has to be carried out in extremely high temperatures, and if you remember my first slide on this, it's the temperature like the sun. Nuclear weapons that use fusion to generate energy, these are called thermonuclear weapons or hydrogen bombs, actually require a small fission bomb, so an atomic bomb, to generate enough heat for this to start to occur. When the masses of reactants and products in a nuclear reaction are measured, the products have less mass than the reactants. The lost mass is converted to energy, and we use the E equals mc squared. Combining the smaller nuclei together to form larger ones is called nuclear fusion. The reactions of the sun and stars are fusion reactions. And the parent isotope in a radioactive decay and in fission is always radioactive, but in fusion, the reactant and product isotopes are not necessarily